Good morning, everyone. So let's get started. My name is 𝗗𝗲𝗿𝗀, and I work for the Building and Property Division of Monash University as the Sustainability Planner. I'm your host for today, and Karen and Nancy are doing tech in the background. So to start, we want to, in the spirit of reconciliation, Monash University and the Monash Energy Institute acknowledges the traditional custodians of country throughout Australia and their connections to land, sea, and community. We pay our respects to their elders past, present, and extend that respect to all Aboriginal and Torres Strait Islander peoples today. So to just remind you, the format of the webinar is 1 hour. We have 3 speakers and then time for Q&A at the end. The session is being recorded, and presentations and recording of the webinar will be available after this webinar at the Monash Energy Institute website. We'll also be sending out a short survey after the webinar, and we'd really love your feedback. So through the presentations and the webinar, at the bottom of the Zoom box, you can see the Q&A feature. So do put your Q&A questions in there. They're going to be monitored through the session, but we will definitely then at the end have a Q&A session. So just to remind you of the topic, this is our 4th webinar in the Net Zero series, and welcome to our 3 speakers. So the panelists are going to discuss commercial considerations around establishing market-based demand response agreements, using complementary DER for renewable energy firming, and data-driven techniques for forecasting large site loads to address demand changes. So Nathan's going to discuss the opportunities presented by the Australian electricity market and how electricity retailers are working with their large customers to leverage these advantages in the renewable energy transition. Andrew is going to provide insights into how Monash is taking a portfolio view of DER with our objective to self-firm, offsite renewables, and monetize its value streams. And Guillaume will address the rise of storage as an essential element in the energy transition to net zero and how data is being used to establish dispatch optimization models for commercial scale batteries. So our first presenter is Nathan. Let me just tell you a bit about Nathan. So Nathan works for ENGIE, Australia and New Zealand. He's also a guest lecturer at Monash. So his role as business developer for ENGIE is supported by 17 years of experience serving the energy transition in Australia, the UK and the UAE. He's a specialist in renewable energy generation and energy management with experience in engineering, capital delivery, operations and finance, delivering solutions tailored to complex customer requirements. His specialty is integrating renewables, conventional energy contracting, and demand-side opportunities into energy partnerships. His experience is underpinned by postgraduate qualifications in power engineering, a master's of project management, and an executive MBA. So welcome to Nathan.
Thank you very much, Kendra. Really appreciate that. So I'm going to talk about the energy market in and of itself, and so many people across the whole spectrum of the energy economy are focusing in on the failings of the energy market, and it's really easy to point fingers because we all live in such a complex and such a multi-layered place when we're speaking in the energy space that it's easy to blame people like regulators or the government because we've got layers of infrastructure, technology, environmental considerations. We've got the energy transition, which we're in the midst of here. And so it's really easy to just, say, oh, the problem's too big or the market is fundamentally broken. How can we possibly solve all of this? And, we need the government to step in or we need a regulator to say that we can do these sorts of things. But the truth is, whether we're on the supply side or the demand side of the market, we're all in the same situation. In fact, all participants in the energy value chain share some level of responsibility or ownership in connecting all of this up to make it work. And this is why I've used the final phrase that you'll see there on the slide, which is winners see an opportunity where others see challenges and risk. So what we have at the moment in the energy market is a country that is in a massive state of flux. And where there is change, where there is volatility, there is also opportunity. And so that's what I'm going to explore a little bit today in this webinar. But it's really important that when we look at the energy market what we see is the supply side is what's grabbing all the headlines. Curtailment of renewables, the enforcement of synchronized condensers for connection agreements on solar farms, and the massive influx that we're having into this transition at the moment is creating a whole lot of challenges that our infrastructure is struggling to keep up with. But the truth is, when you're looking at any Keynesian market, is the supply side is really only half the story. We also need to look at what's happening on the demand side. And I've chosen a picture there of what we hailed in South Australia as one of the most amazing days in the history of the energy economy, when the whole state was run by solar electricity. But what you really see is that more than half of that solar energy that came for those few minutes around 1 o'clock was from behind the meter, was actually demand that was taken out of the market to allow it to achieve that outcome. So when we look at the energy market, we need to consider both sides of the equation. We're also in a state of massive transformation. And I'm not going to go into the economics of the duck curve. It's been done to death, and we all understand that energy prices will hollow out during the day as we go because of the penetration of both utility scale and rooftop solar penetration. But I've chosen to analyse the data here for us from 2 years, only just a couple of years apart, and I've focused in on Victoria. So looking at the data from 2017, now, bearing in mind, this was the year that the Hazelwood Power Station closed in Victoria. So it was also, up until that time, a year of unprecedented volatility. But then comparing that to what we saw last year, and we're still seeing this massive opportunity that's associated with these high prices. And when we transfer that data into a relative price duration curve, what we can see is that the standard deviation from the 2019 data, so this is taking into account the penetration of solar PV and the volatility that brings in the market, is much, much greater. So that means that the opportunity for investment is also much, much greater. But that in and of itself poses a number of challenges. And what I wanted to do was just zero in on the last 4 intervals in this chart here. So effectively, the highest price on average 2 hours of every day. And comparing 2017 to 2019, what you're actually seeing there is a massive step change in the load weighted pricing of those 2 hours of the day. So from 2017, you would already state in a normal stable market condition that a load weighted price or a load weighted ratio of 1.25 was favourable. But now we're living in a world where we're seeing an average load weighted price across the entire calendar year of 1.75. So delta of 40% uplift in the value of electricity there. This has massive economic ramifications for investment in generation. And what it is actually a warning signal for for gentailers to consider the broader context before the investment is committed. So because we've got such volatility, because the value is concentrated to such a short period during the day, the actual marginal cost of generation is obscured. And so what this means is if you're basing your investment off, just these 2 hours of the day or so, what we're seeing is a skew between OPEX and CAPEX. And something that this can precipitate, or one of the modelled outcomes, would be a divergent cobweb model of economics, whereby businesses, generators are overcapitalising in investment for what could be possibly a merchant or high risk return. But what I want to do is just turn this model around. And so looking at it from purely a demand side opportunities perspective, which is completely different from the linear or the marginal cost of generation model. So what we see with demand side response is short duration, short notice opportunities based around what the prevailing market is doing. And the cost of participating in those actions is very different to the potential revenue outcome. What that means is that the variable costs associated with competing in this market are not necessarily proportionate to your input, because what you're doing is when you're participating in demand side response, you're looking inward. You're saying, well, what can I go without, or what can my business do? How can we change the way we relate to energy in order to avail ourselves of this opportunity? And so some of the things that ENGIE is doing to support the energy transition in this space is the three pillars of our operations here in Australia at the moment. And we call it the 3Ds, being decentralisation, decarbonisation and digitisation. And actually these three pillars work in harmony with each other to optimise the outcome, or to lead the transition to zero carbon. Decentralisation is about the transition away from point of generation, transmission and consumption to generation or energy management that is dispersed throughout the electricity grid. Decarbonisation speaks for itself, but in our context, it's about pivoting from our capital and the equity that we've already placed in large-scale point of generation sources like coal-fired power stations, and repositioning that equity in low-carbon wind and solar farms, or even dispersed throughout our customers' premises, whether that's in low carbon, behind the meter generation, firming capability, those types of opportunities as well. But the thing that underpins all of this, the thing that brings it together, and really where we're going to be looking in this webinar about the forecast of the market and where the opportunity lies, is in how we can actually bridge this gap. And the key to that is digitisation. So that is utilising technology to get from the reliable legacy of these large, cumbersome coal-fired powered stations into a new era where we have flexibility and we have the capability to use energy as we need it and to respond to market forces rather than being price takers. The phrase that's being used quite a lot is prosumer. So how does an energy user go from a consumer, someone who signs a contract, takes a price, to being a prosumer, so someone who acts with purpose and achieves an outcome rather than just being beholden to the market? And we do this across the spectrum of the energy market. So in generation, it means the diversified portfolio looking to wind and solar. In terms of supply, it's about managing the contracts and agreements that facilitate all of these opportunities to happen. So how we do our wholesale portfolio management, sourcing electricity, sourcing renewable certificates, and how does the customer engage with that? How do we create this ethereal market concept into an agreement that a customer can sign and then be confident that they've engaged with the product that they've bought? But finally, we look at the demand side. And this is where things start to get really interesting, and there's a whole lot more levers that we can pull. So obviously we're looking at what's happening behind the meter in terms of generation, storage. Another technology emerging in Australia is district heating and cooling. How can we avoid the grid emissions associated with electricity consumption? But then what is going to be the optimal time to engage with this? How can we do this in real time in a real world? And I've categorized this into three parts here. The first one being load management. So when do we use our power? How much do we use? So energy efficiency, what level of asset redundancy do we have at our disposal? How do we automate it? And how can we control it to the nth degree to get the absolute maximum resolution possible in control? But then stepping away from the management side into the response side. So how can we do things quick? How can we respond? How can we be agile and flexible to be able to achieve the price outcomes and access the benefit of that 1.75 load weighted ratio that we saw there? Well, first of all, we need the platform, we need the technology to do it, but we also need the agreements, the contracts to be able to commercialize it, to be able to actually create revenue from it or offset costs in another in another market. So balancing that equation between the input cost and what it's worth to us. And then energy storage also has a role in this. And one of the wheelbarrows that I love to push is that energy storage is not just around batteries. I mean, yeah, batteries are easy, they're quite compact, they're a relatively mature technology, even as the economics is still catching up with it. But there's so many more things when we look at energy storage. So water corporations have been doing it for centuries, where they pump water when the price is cheap, and they gravitate when the price is expensive. Businesses are built with storage inventory silos so they can schedule production around opportunities. And then also thermal energy is a big part of the equation too. So pre-charging venues, storing heat and cold when energy is expensive, or when energy is cheap, to release when energy is expensive. So essentially what we wanted to demonstrate here was the market has a whole range of different options and opportunities at the moment, which has been, it's all part and parcel of the energy transition. But there are also a number of ways that businesses and institutions can engage with this opportunity and make the most of it in looking behind the meter as well, given that demand is literally half of what's in the market. Thank you very much.
Great, thank you for that, Nathan. Right, so moving on, our second speaker is Andrew Pintar, who's the manager of Microgrid strategy and commercialization at Monash University. And Andrew is leading the effort at Monash to establish commercial arrangements with external market participants in order to monetize existing and future DER, including building loads. So within this, the Microgrid Market Operator Project aims to demonstrate how value can be ascribed back to internal microgrid customers. So Andrew has over 10 years experience, including developing strategic insights and commercial opportunities across renewables, and in a previous life worked in investment markets, analyzing listed companies across the energy value chain. So welcome to Andrew, and look forward to seeing your slides.
Thanks for the introduction there, Kendra. I'm just going to share my screen here, and hopefully that, that doesn't take too long. Apologies for the delay. Okay, hopefully you can all see them there. Again, as Andrew said, and as Kendra said, and as Nathan sort of got into, there's opportunities in terms of the transition that the energy market is undertaking, and Monash, as a large energy customer, is looking at those opportunities. And really, the thrust of this presentation is to talk about how the journey that Monash has gone through and is continuing to go through to monetize some of those values, and then also how we really see ourselves as in some degree a leading light for opportunities that other commercial and large energy users can follow in terms of going towards their own net zero targets. So the title really is coordinating the energy flexibility, and in part to achieve PPA firming, but there's more to it than just that. So just to set the scene a little bit, Monash University has the net zero objective, which is to have zero carbon emissions by 2030, and a large part of that is through procuring 100% renewable energy. That gets us about 3/4 of the way to net zero by 2030, and then there's additional things that we can do. So we've already actually achieved, in effect, 100% renewable energy through a wind farm PPA, and I'll talk a little bit about how what we're doing with that, and how we're going from being 100% across a year in terms of renewable energy to as close to 100% in all time stamps, or in all time slots. So a big part of that, and Nathan alluded to it, is to demonstrate how the whole energy system will be 100% renewable energy. It requires a transition of energy consumers to be not just passive energy users, which they've historically been, but to move towards a more active style of consumption, and that load flexibility is a substantial part of that. So for ourselves, we're concerned with not just reducing our carbon intensity to zero in 2030, but also in terms of managing the cost thereof, or reducing the cost of energy. And that's two-sided as well. That's both reducing the cost, but also optimizing or taking advantage of the revenue opportunities that are available as the transition is undertaken. And so we see ourselves on that journey and moving towards a direction. A part of that, as Nathan suggested, is that we have our own behind the meter resources, so rooftop solar, but then also we continue to increase our on-site storage. We've got some already, and we'll continue to deploy that over the coming years. And we think that ultimately there's a megawatt scale, like multiple megawatt scale requirement in the context of our site. With a peak demand of around 18 megawatts, that's not immaterial. But then also the transactive energy aspect of the microgrid for the load flexibility part is important too. So to dig it a little bit deeper, really our own situation at Monash is effectively a case study for a lot of what Nathan touched on. We're a consumer of about 100 gigawatt hours of energy, or electricity rather, per year. We'll get some gas on top of that, and that will over time be fully electrified. Around 2/3 of that is at the Clayton campus, and the shape that is shown there in the top right-hand corner is there's 4 lines, and 3 of them really that are the most interesting. So what we're showing there is how the load at Monash is not dissimilar to large commercial industrial type profile things. That is what we actually are, but really akin to sort of offices and sort of mix of residential as well, not industrial in the classic production sense. So we have our average consumption in the blue line, which is the average across the year. The black line demonstrates what the average consumption across a day is in the summer months, first quarter of the year, and the red line shows what a peak day looks like. So that's is sort of the difference between the blue line, our average day, and a peak day in summer really represents the increment that's resulting from heating and cooling demand, or rather cooling demand, so air conditioning, on hot days. So how do we then consider how we go from having 100% of our total electricity consumption in a year being from renewables to being close to that in every timestamp? So if we look at the bottom right chart there, what we've shown is, and there's a lot going on in that chart, in the black is the percentage of our load on a given day across a week, or rather in given half hours across a week, that's being covered by the generation of the wind farm that we have an agreement with, which is 𝗗𝗲𝗲𝗗𝗏. We have a PPA there, and that PPA effectively gives us implied spot price exposure. I'll get to that in a minute. So we can see really what the important takeaway from that chart is, that on any given half hour, anything between none of our load to sort of 3.5 to 4 times our load is covered by the instantaneous generation from one single renewable asset. We're concerned with getting that to a more stable figure in all time spots. So one way to do that is to consider generation diversity. So that's answering the first question. How do we move towards being closer to 100% renewable coverage all the time? So if various studies, if we sort of think about what the NEM will look like as we approach 2050 and 100% renewables, multiple studies have indicated that the generation mix will be something in the order of 70% wind and 30% solar, or 2/3 and 1/3, there or thereabouts. Noting that the NEM as a whole has substantial interconnections between states, resource diversity across states, both in terms of wind, solar, and locationally, hence the creation of renewable energy zones. So Monash is really a microcosm of that, but a not insubstantial microcosm. If we think about our own case of having 70% wind and solar and moving in that direction, what I'm indicating in that chart on the top right is how in a probability weighted sense, or a distribution weighted sense, we have an increasing portion of time where instantaneously we have more closer to 100% of our load, both below and above, but more close to 100% alignment of our load being from renewables. That results in ultimately less requirement for firming of that renewable energy for ourselves, and then ultimately from a system-wide sense, the requirement for firming down the track. So in an annual basis, the alignment increases from about sort of 60 to 65% when you have a wind only, in terms of relative to load, to about 80+% when you have a wind and solar mix. So then the question arises, really, which is the crux of this presentation, is how do you balance the remaining 20%? And as Nathan's alluded to, there's load flexibility and storage is the conclusive answer. So what does load flexibility actually achieve? Well, as Nathan indicated, the energy market's adapting to the extent that there's an increase in the types of agreements being developed by retailers to share some of the value of this load weighted price that's 1.75 times the average across the year, and aligning aligning the load to renewables helps you attract some of those, or extract rather some of that value. So from the first side, it gives you greater degree of price certainty. So given a renewable PPA is a long-term agreement with an asset, typically 10 years plus, in simple terms, the greater portion of that energy that is generated from that renewable resource and instantaneously or simultaneously aligned with a load, irrespective of whether there's a cable directly to the load or not, which is clearly not the case, but by the virtue of the way that the financial arrangement works, this having a greater degree of instantaneous consumption to the renewable generation allows you to lock in a larger portion of that steady price, irrespective of wholesale prices, because you already implicitly have a spot price exposure through entering the renewable PPA in the first place. It also allows you to implicitly have a greater degree of indirect prioritization of that zero renewable energy through the structure of the market itself. So if we then move towards coordinating wholesale prices and demand charges, or rather how we flex that load for coordination of wholesale prices, we can think of ourselves as being on a journey. And on the top right there, I drew some encouragement from Nathan's presentation that cartoons are cute. You can judge for yourself where you are on that journey at any stage. It might feel different. But effectively, implementing demand response allows you to, by first having a low risk toe dipping exercise, you can have a greater degree of de-risking the journey towards spot exposure. And there's ways to consider that. There's some issues in terms of setting the baseline, which we can go into another time. But effectively, being largely temperature dependent needs to have some smarter consideration of how you set that baseline. Then if we sort of move to the last addressable or immediately obvious addressable value stream, and I promised I wouldn't use the term value stack in this presentation, but the last of the addressable value streams that are immediate is managing our own peak demand profile. Guillaume will address this in some greater detail at a data level in his presentation. But if we just sort of look at what the context for Monash is, we have a load duration where 1 to 2% of the total periods in a year represent an increment of around 40 to 50% of our peak load or peak demand in a half-hour period. We pay materially for that. It's in the order of that increment in that 1 or 2% represents in the order of about $500,000 plus in increased demand charges. That'll vary for customer depending on their tariff and their DNSP. But for us, it's about $500,000 for about 6 megawatts of peak that occurs on a handful of occasions. The top chart represents the peak per day across the year. So really flattening those peaks off by using multiple resources is the objective. Then finally, and I'm getting the wind up in the background here from our hidden away technology people, is how does demand flexibility or load flexibility achieve those ends, and what's the actual outcome? And so there's some questions to resolve. For a start, there's a tension to some extent between, do you implement chemical storage, so batteries, which are mature and the economics are coming down? Do you implement some other types of storage? So naturally on a site which has large degrees of heating and cooling load, that results in building-based thermal storage. And then you've got to ask yourself is, to what extent and what duration can you defer consumption either forward or later into a day from those buildings, whilst retaining comfort and rewarding the internal participants? So that's only touching on it here, but that's the essence of what we're trying to achieve with our transactive energy market, or answer that question through our transactive energy market experience. And then ultimately for the economists out there, what's the cost structure or the marginal cost of that flexible load? So we aim to eventually get to some sort of cost curve, marginal cost curve, as is shown on the right, of both abatement, or ultimately abatement, but really the marginal cost of that load flexibility. And that's represented in a real world sense in terms of the cost of implementing physical devices, and then the reward mechanism that you implement to those flexible loads. So that's it for me. Thanks again.
Thank you for that, Andrew. Right, moving on to our final speaker. We have Guillaume Roger, who's the Associate Director and Theme Leader of Markets and Policy at the Monash Energy Institute and in the Faculty of Business and Economics. So Guillaume is going to talk to us, delving into more detail on batteries and data-driven decisions. So his research focuses on incentive design, which finds applications in market design, compensation contracts, security design, and in the economics of regulation. His work is published in international academic journals such as the American Economic Journal Microeconomics, Games in Economic Behavior, or the Journal of Mathematical Economics. Guillaume has received multiple grants, including the Australian Research Council Discovery Project grant, and he's been invited to well over 50 seminars, conferences in the last 10 years in Australia and overseas. So welcome, Guillaume, and over to you.
Well, thank you, Kendra. Good morning, and good morning to our friendly audience. So I'm going to essentially pick it up from where Andrew left it and speak specifically about a project that we are running at the moment on the Monash campus, and then extend that to the broader markets to conclude. So specifically, I'm going to speak about storage. This is a project which is supported by Andrew's team. We use the campus as being a real life lab, if you will, and in doing that, we try to address some of the questions that Andrew has raised just now. All right, so big issue in electricity, as we know, for most of us, is that it cannot yet be stored, at least meaningfully stored. This is changing very fast, as we know. Power flows must be balanced at all times, which creates all sorts of physical problems on the grid. That in itself may not be a problem, except for two little facts. One is that consumption fluctuates over time as well. The fact that consumption fluctuates, at least at an aggregate level, is reasonably predictable. But now with penetration of VRE, supply also fluctuates. And those fluctuations in supply, it turns out, are much less predictable than fluctuations in demand. So now we have stochasticity on both sides of the market. And to make matters worse, moments in which we have peak supply do not match moments in which we have peak demand. So we've seen the duck curve. Nathan has explained in some detail that this is exactly when we have the most supply, that middle of the afternoon, that we demand the least electricity as well. So this doesn't make it for an easy problem, but thankfully we have a new device, which is storage, which greatly helps addressing all of these issues. Storage at Monash is this. We operate on a microgrid. We have 2 storage technologies. One is lithium ion for those interested. The other one is vanadium. We're also connected to the main grid, of course, as Andrew explained. We're backed by a retail contract at present. The details of these contracts are evolving as we speak, but by and large, we're still connected to a retailer. And we generate some of our own power through solar panels. And so part of the exercise, of course, is to forecast the production of the solar panels, which can be a little bit finicky at times. All right, so what is the challenge in operating storage? So at the conceptual level, it's very simple, right? We all know that. The only questions that we are really interested in answering is when to charge and discharge. So of course, if you want to arbitrage prices, you want to charge when it's cheap and you want to discharge when it's expensive. Conceptually, as I said, this is very simple. The devil, as ever, is in the details, right? The nature of the problem is, in fact, a little bit more complicated than it appears at first, because those charging and discharging decisions depend on a bunch of things. They depend in particular on the state of charge. So to make it really trivial, of course, you cannot charge if you're already fully charged, and conversely. So how much you can charge depends on what you have in the tank, just like when you drive a car. But also it depends, those decisions depend also on your expectations about the future. So will I need a lot of power in an hour from now, in 5 hours from now, or can I go crazy right now and discharge all I want? Right. So this, in terms of mathematics, this is a dynamic optimization problem, and on top of that, we may be subject to a bunch of constraints, which I'll explain in a moment. So these constraints are twofold for us, or these challenges are twofold. One is, as Andrew explained, we are subject to network peak demand charges, which means that if we exceed a certain level of power usage at any moment in time, we are being charged a certain amount by our network service provider that we have to carry over for 12 months. So this is a very costly exercise, right? A minute increase above the peak demand that is already established carries over for 12 months. And so this marginal cost becomes really, really expensive. The second challenge that we face is the forecast of net load demand. And the reason is not so much that load itself is difficult to forecast. My friends in econometrics tell me that this is not. What is rather more difficult is to forecast VRE production, so that we have a net load forecast. All right, so let me explain in a couple of pictures. So the first problem is peak demand charges. And so there we can see that broadly we have a problem of height and duration, right? So if you think of the red line being the currently established peak demand level, then the question in front of us is, how much more are we going to consume, or can we expect to consume beyond this peak demand already established? And the other question is, for how long, right? So on the left-hand side, you have something which is abrupt but brief, and then on the right-hand side, you have something which is a little bit smoother but lasts longer. Right? Now, of course, the point is that we have only so much energy as there is surface under that curve, right, between the blue curve and the red curve. Okay, so that's the energy that's available for discharging at that point, that arbitrary point in time. And then the question is, do we discharge very fast for a brief while, or do we have to hold up for a time? Okay, so this is where the net load forecast becomes very important, in particular, the solar forecast. So at this point, we have about 95% accuracy in forecast, and this is using a very parsimonious model. So 95% sounds good. If you say 95% to most people, let's say that's a good performance. And then you ponder it and you realize you're completely wrong at least one day of the month. If you're completely wrong at least one day of the month, those peak demand charges are going to be very steep indeed. Right? So we need to do much better than that. We need to get to 99 or 99.5% accuracy, I think. So those forecasts entail also a technical difficulty, which is that we have to forecast the maximum as well. Right? So not only we have to forecast the entire ramp up of of net load demand, but also the maximum load demand at any point in time. Okay. So the environment on the cost side for us is actually quite simple, and so that part of the equation is actually very straightforward. At present, we're exposed to a tariff in two parts. So it's not exactly a two-part tariff, as economists would say, but this is a tariff in two parts. There is a peak period and an off-peak period, and so it makes a lot of sense from there on to systematically discharge during the peak and systematically charge off-peak, of course. This is changing fast as well. We're being exposed more and more to financial incentives to reduce consumption during the day. So we're facing trade-offs now as to exactly when to charge and when to discharge, right? And so going forward, Andrew tells me we'll be fully exposed to wholesale prices. And so we'll engage in something which is a bit more subtle. Not only we'll try to manage our peak load demand right at that peak, as I tried to explain, but also we'll have to engage in energy arbitrage. All right. So this is storage at Monash, and which leads me to speak very briefly about storage on a broader scale on the grid. Storage can do a bunch of wonderful things for us. One is the intertemporal production of, intertemporal substitution of production. So you can produce energy at 2 in the afternoon, store it, and then deliver it at 7 when you actually need it. That's reasonably obvious. It can help also in ancillary services, such as firming VRE for dispatch. So you may change from being non-dispatchable to dispatchable if you have a battery attached to your VRE facility. It helps with frequency control services. It helps by supplying what's called synthetic inertia, for example, as well as voltage control. And of course, you can engage in energy arbitrage, which corresponds to taking advantage of this duck curve that Nathan showed a bit earlier. So all of this is very attractive. It entails a whole bunch of challenges. What's an accurate market design for storage in the energy market? At present, we don't know. This is difficult because, as I tried to explain, storage has dynamic strategies. So questions to charge and discharge depend on the state of charge, depend on future expectations. Are we going to continue making distinctions that are maybe somewhat artificial now between FCAS markets and energy markets? After all, this is all electricity. What does a dispatch engine look like when you have dynamic optimization as a problem rather than a linear programming problem? There's a further question of market boundary. TNSP are investing in storage, and so therefore do we want to continue separating energy from transports? And with this, I'm going to conclude because I believe I may be over time. So here are my details. Thank you for your attention and your interest in this.
Thank you, Guillaume. Great, so now we're moving into the Q&A section of the webinar. So if I could get, yes, all the speakers back and Andrew, get your camera back on. So you can tell it's just before lunch because you've been quite quiet in the Q&A box, everyone. So I'll start off with a couple of questions. So one for Nathan. So you showed us that looking at those price curves. So how do you see the price duration curve for the top 2 hours evolving in the next 1 to 5 years?
I think we're likely to see the load duration curve becoming far more pronounced, i.e. those top 2 hours of the day will be higher and the bottom 2 hours of the day will be lower. But I think what we will see is it'll be a step change. The rate of growth in that curve will not be quite as steep. The curve will be quite a lot more of a step. The reason or the fundamental behind that will be because we're likely to have, wherever there's value in the market, you're going to have participants capturing that value. You're going to have people, whether it's battery side demand response or whether it is through load curtailment or standby generation, wherever you've got high prices, the market will respond to those high prices. So I guess the the future is that the high prices will be higher and the low prices will be lower, but the intermediary will be less pronounced.
Cool. Thanks for that. And I suppose leaping off that question, one for Andrew. So you showed us about Monash's ability for capacity for firming, but just thinking through that and what Nathan said about how the price curve is changing, and what do you think, at what point, I guess you can all answer this as well, does investment in storage make economic sense as opposed to doing other load shifting activities?
Yeah, sure. That's always a hairy one in a bunch of from a bunch of different perspectives, and I don't have a good dollar per kilowatt hour metric. I know in the US, $100 per kilowatt hour for battery energy storage at the cell level is often discussed, and we're seeing various large battery manufacturers move towards that and even project lower down. What we're sort of seeing from our own experience and others of similar size, where they're implementing, say, single-digit megawatt scale batteries, is that the cost of implementing the full system is not $100 per US per megawatt hour per kilowatt hour. It's a few times more once you integrate the BMS and integrate into existing systems and convert to Aussie dollars and all that sort of thing. So I think we're getting to, in simple terms, I think we're getting closer and closer to that. But really, the only question, the question isn't solely one of what's the battery cost before it's economic. It's as most people should hopefully be aware to some extent, it's the value of the what you implement in storage and what value streams you address, and the extent to which those value streams conflict with one another. Hence the both Guillaume and Nathan, I think, addressed the fact that it's there's a co-optimization consideration. So as Monash, sort of taking our own perspective again, as we move towards considering implementing additional storage, as I indicated in our presentation, peak demand is one where for us is an addressable area, although there's a consideration around the duration of storage that's required. And then as we move towards a greater proportion of our energy being aligned to renewables and that low price period, taking advantage of those peak prices that Nathan discussed just now will be a big part of it. So price arbitrage will, I think, over time become a greater percentage of the value stack for us. I swore I wouldn't use that term, but it's hard to avoid. But currently, peak demand charges is also considerable, and then obviously FCAS, which is not a focus of today's discussion, but that's there in the short term. So I think in short, we're getting closer very quickly. And it'll make sense for different people at different times, but we're just on that cusp, I think. Can I
just add to Andrew's comment there? It's very easy to look at this sort of technology in terms of kilowatts, kilowatt hours, kVA. But the truth is, from a commercial perspective, you need to look at it in terms of revenue options. And so when we talk about firming, or when we talk about the value stack of a battery, as engineers, we jump to a technical solution, but the truth is, it's what revenue can we access through that, and then what liability is that revenue offsetting as well. So the actual answer is not necessarily an interval by interval or a kilowatt by kilowatt answer, but a commercial answer.
Okay, thank you. And we seem to, Guillaume unfortunately has dropped off. He's having connection issues. So we can pass on any questions there's a couple in the Q&A for him. But I suppose building on this, what you've just been talking about, Nathan, there's a couple of questions, specifically around ENGIE and from a retailer perspective. So wanting to know the potential size of demand response market in Australia, and then what ENGIE is going to be doing in that space.
Well, it's probably easy to answer that back to front, in that already we work with our C&I retail customers to commercialize demand response. So we have demand response or load reduction agreements, and these are actually quite flexible instruments that can be tailored or suited to an individual customer's needs. Also, it's important to look at the context of ENGIE in Australia as well. Is what we see ourselves is leading the energy transition as energy as a service, as a precinct scale partner through things like our Better Cities program, through the various alliance agreements that we have. And so demand response for us really works, it comes in it from both sides. One, the ability to commercialize demand response, but also the ability to work with our partners to, because, for example, if we were to work with an educational institution, we are not educators in and of ourselves. So we don't necessarily know the individual pain points or pressure points that a customer has, but we can work with them to help amplify the benefit of their response too. And look, and in terms of the size of the market, what we're seeing at the moment is there is a massive skew towards the right side of the price duration curve. As we've said, we're trending at 1.75 above the mean. So that means that there's nearly double the value associated with those few intervals in the day that's there to be captured. And so the market's going to reach an equilibrium where, with wholesale prices cannot continue to skyrocket because the value is there for customers to capture. What is that value? I can't speculate on that, but what we'll see is an equalising. Wherever there's money, the customers will flow to that value.
Great, thank you. And Guillaume, since you're back, I'm going to throw one of the questions that is to you while we have you. So it was to Andrew and to Guillaume, but you both had discussed Monash's viewpoint and a bit of our PPA provider. So the question is, what about the relationship with the local DNSP, and is there any value, or what is the value in that relationship?
So I'm going to defer to Andrew for these kind of questions. I really have no idea. Okay,
Andrew.
Yeah, the context, that is a good question, and certainly one that's on our minds in relation to how can value be ascribed from the benefits provided to the network from distributed resources. The context we have ourselves, and I'll start at our site and work outwards. We're in the United Energy distribution area. We have a couple of dedicated pieces of infrastructure that go directly to us. So we don't necessarily have the dedicated feeders, so we don't have any low voltage related constraints that we can solve. We basically run our own HV, LV network internally to the campus. Where we could potentially, and this is, as you go higher and higher up the order of the distribution grid, you get to greater magnitudes of problems that need to be solved, and also greater complexity. But the potential sits there for resolving substation-related concerns. Now, again, it's been a little while since I've looked at substation constraints, but to the best of my knowledge, there's not anything substantial in the Notting Hill, and I think it's I forgot the name of the other substation that we're connected to. I'll have to get back to you on that. But there's limited opportunity for us to directly participate in resolving network-related issues. But certainly, as far as the market's concerned, more broadly, as far as distributed energy resources, we do think that there's certainly advantages to assisting the networks, but that requires a coordinated player to do that. So maybe not us in the immediate future.
Great, thanks for that. Continuing on with you, Andrew, lots of questions for you, but Guillaume, this might be because it's a sort of data one as well, but Steve has asked that obviously Monash mentioned that us as Monash, we're trying to optimize our energy use storage with the goal that at any one point we can say we're powered by renewable rather than just aggregating over the year that we buy enough renewable to cover what we've used. So could you talk about how we're going to measure or achieve this, and are we going to use any kind of software, or how are we going to actually,
That was to me, wasn't it, Kendra?
It was to you, yeah.
So The short answer is yes, that is the intention. Ultimately, we'll look to have from our wind farm, so 𝗗𝗲𝗲𝗗𝗲 out in Western Victoria, we'll look to have a live SCADA connection directly from the turbines that are contractually attributed to our PPA, so that we can in real time see the generation. Currently, we receive generation for settlement purposes on a weekly basis. Obviously, we can't. We can't influence our load going 1 week back, so and it's some weeks delayed as a matter of fact. So we are looking at how we would have a direct SCADA. We're in conversations with our with the developer there, how we would have a direct SCADA connection to our own, well, essentially our own building automation system, which has an overlay into the microgrid, and so how we would align on-site demand to maybe not perfectly initially, but to move towards having greater temporal overlay between production and consumption. So things like implementing SCADA from there, and if we were to add on additional solar PPA, we would look to do the same, and then on top of that, implementation of storage to assist in that alignment. So those are to the point, and we haven't touched on non-renewable generation, but we have a little bit of gas-fired generation on site as well, which we can also use to implement to manage that as well. So those are various strategies that we're looking at.
Great. Nathan or Guillaume, did you have? Sorry, nodding along with Nathan, but anything you wanted to add to that? Or
no, I don't have anything to add to that, but I did see questions in the chat, and unfortunately I'm back to back with another obligation, so I'm going to pick it up before you even ask it. So there was somebody asking about two-sided markets or consumers bidding as well into the market, and so I don't think it's going to happen exactly like that. Nonetheless, it is the way of the future, so we need to restore, we desperately need to restore elasticity in demand. Right now we have an artificially inelastic demand. This is why, in part, we observe all those high prices. So the way this may be implemented is through real-time pricing or variations thereof. So that means measuring your electricity consumption over the course of the day and charging something which is connected to the real cost of supplying the power, which reflects the wholesale market's price. So the way this could work was to install smart meters, implement real-time pricing, get the retailers to turn into what's called scheduled loads, and make their own, express their own demand function in the wholesale market. And so once we have a little bit more elasticity in the market, I expect that we'll see better price behavior. This is a very important aspect of the energy transition, I think.
And I was just going to call that question out too. I really saw it and I liked it. I think there is a principle behind it though, and it relates back to the meme that I shared of the two Spider-Men pointing at each other. Is you can vote with your feet, and that's the whole point of demand response. If you don't want to participate in the market at that price, then switch it off. But I think where it's going to become far more a capacity market may offer some more advantages around that space, but again, that will involve the complete fundamental shift in the way that we engage with energy as well. But certainly the idea that you have both buyers and sellers bidding for the same capacity at the same time is a very good way of balancing out the economic metrics there.
Great, thanks, Nathan. So I was going to say goodbye to you, but I know he had to leave promptly at 12 o'clock, and it is 12 o'clock, so our hour is up. There's a couple of questions we didn't get answered, but if you want to follow up with any of the speakers, you could look them up on LinkedIn, send them a message and follow up with your questions. So in closing, I just wanted to again thank our three speakers, Nathan, Andrew, and Guillaume, for sharing their knowledge and insights today, for opportunities for retailers, customers, presented by the electricity market and the transition to net zero, and as well as the role of energy storage and data. And just as a reminder, you will get a survey after this that it would be great to get some feedback for you, and otherwise have a lovely lunchtime.